All right. So first things first, you have an exam coming up in this class in 1 week. Yes. What's that stuff? You know, numbers, equations, that sort of thing. Seriously, it'll go through second order systems. First order, second order. Time constants, zetas, omega naughts. If that's what that is, yes. I think that's right. Yeah, chapter 7 and 8. Chapters 7 and 8. You should expect... my exams are open book and open note, but that doesn't mean that they're easy. I like to place a high premium on trying to like conceptual questions, things where like your intuition is more helpful than your ability to do like 3 pages of calculus. That's sort of those are my favorite kinds of questions. Although I usually throw in one like calculus question just so that, you know, the people who are only good at calculus have something to hold on to. I've not taught this course in a long time. I've only taught it once before, which means that I don't have a whole bunch of old exams to hand you. I can dig up whatever I had when I taught the course in 2006. Yes, I taught this once as a summer course in summer 2006. So I think I still have that old exam somewhere, and I'll post it. But that's what I got. So let's see what else I need to tell you about the exam. I may try to move it to a different room because, especially if it's open book, open note, like it's nice to spread out your stuff a little bit. And we're kind of bunched up here. So I'll get back to you on where we're going to take the exam. Sound good? Questions? Yes. It's next Wednesday. This time. Maybe not this room though. Okay? Everyone's going to be here? No excuses? Okay. All right, well, let's talk some math. So we're on to chapter 8. Is 8 the AC signals one? Okay. So everything we're going to discuss from here on out is AC analysis, cosines, okay? And there's a very special reason we're going to spend a lot of time talking about cosines. There's one special function about, special property about cosines, and that is this. So let's just say for the sake of argument, I gave you this circuit, okay? And I'm going to mess around with the input signal that I put in. If I put in a square wave, what's going to come out the other end? What's going to be the output signal? Like if my input is a square wave, what am I going to get as an output? Yes? A what? Mini time constant. So if I put in a square wave, it's going to charge and then discharge and then charge and then discharge. That's cool, right? We learned how to, that's our first order system, right? What if I put in a a triangle signal? What do you think might come out? I don't know. It'll be something that looks sort of like this, but it'll be a little bit rounded maybe. Anyway, I don't want to dwell too much on that. But there is one really interesting property, which is that if you were to take that circuit and drive it with a cosine, the signal that comes out at the output would have a very special property. Yes? What's that? The phase is part of it, but there's something more fundamental than that. Okay, and it is this. If your input is a cosine, your output will be a cosine at the same frequency. Okay? So this is like fundamental. This is sort of like the heart of it all. This is why we spend so much time worrying about cosines. Cosines have this magical property that no other signal has. Like if you take a square wave and put it into this circuit, did you get a square wave out? You did not. If you put a triangle or a sawtooth in, you get a triangle or a sawtooth out. You do not. Cosines have this magical property that if you put a cosine into a circuit, any linear circuit, so linear means resistors, capacitors, and inductors, which is basically most everything, okay? If you put a cosine into a circuit, your output will be a cosine at the same frequency. That's a really fundamental property of circuits. Output at the cosine at the same frequency. The only difference is that your output cosine has the same frequency, but it'll have a different amplitude. So amplitude means it might be shorter, like, might be smaller, or it could be bigger even, okay? So it'll have a different amplitude, and it might have a phase shift. Okay, that means that it might be shifted to the left or to the right relative to the original signal. But it will be a cosine, and it will be at the same frequency. And that's pretty powerful stuff. Okay? So because of that, we're going to spend a lot of time worrying about what happens to cosines as they go through circuits. Because if you can understand how cosines go through a circuit, then you can start to talk about filters, high-pass filters, low-pass filters, because you can think of the different frequencies in your system, and each frequency is basically just a cosine. Okay, so far so good? So we're going to develop the math to deal with this. Right? So in essence, let me just stick with our RC circuit that I have up there for a second. And I'm going to explain the problem that we're trying to solve. So, do you all remember, we solved for the differential equation of this circuit, did we not? Does everybody remember it? It was something like V out prime plus 1 over RC V out equaled 1 over RC V in. Is that correct? I'll give you a hint. It is correct. Good. Now, before, like 2 weeks ago, we solved this problem taking into account that our input voltage, our input signal was just a constant. Like it was 0 up until time t equals 0. And then it just went to a constant value of 1. And we solved that, right? We did a differential equation. We've got a particular solution. We got the homogeneous solution. It was like pages and pages of math, and everybody got tired. But we solved it, right? We figured out that the response to this circuit is some sort of signal that looks like a, like a decaying, so like a charging capacitor, and the rate of charge is set by the value of the capacitance. So we're essentially still interested in solving the same differential equation. Okay, because this is it. Like this differential equation, that always has to be true for this circuit, right? It's not just true for certain inputs. It's always true. The problem now is that instead of having this nice situation where my input is a constant, now I have this awful situation where my input signal is a cosine. So k cosine omega t, let's say. Blech, right? So that's not a pretty thing. So now we have to figure out how to work this problem. And there's derivatives involved, and taking derivatives of. So remember what we did before is like we did the guess and check method. Well, when we had a constant, we guessed that when our input was a constant, we guessed that our output was a constant. Over here, it's a little bit more complicated. If we guess that our output is going to be a cosine with some different amplitude and phase, then we've got to take the derivative of that expression and sub it into here, and the derivative of a cosine is a sine, and then there's phase. It's just awful. The math gets very ugly very quickly. So we can certainly solve it using the guess and check method. Right, so essentially what we could do is we could guess that V out is going to be some cosine at the same frequency with some phase shift, And then we could say, well, if that's true, then V out has to equal whatever. And then we could substitute all of that back into the differential equation and see if we could solve for magnitude and phase. You can do it, but holy smokes, it is not pretty. Okay? It is ugly, and it's just not the most efficient way to go about it. The longest piece of chalk up here is about ½ an inch long. Oh, here we go. This one might be a bit better. No, it's not really any better at all. Okay, so what we're going to do is develop some math skills that's going to make it easier to solve this differential equation for cosine inputs. All right, we could do it this way. Guessing V out, getting V out prime, subbing it back into the differential equation and figuring out what magnitude and phase you would have to have in order to make this work. But I'm telling you, I've done it. It's ugly. It takes lots and lots of math and it's slow. Yes? What's that? Yeah, m is the amplitude of your cosine, but then you still have to figure out if you're, a formula for it, because it can't just be any old value. The circuit dictates what the value would be. Okay, so everything we're going to do is motivated around solving this same differential equation. So here's what I want to do. We started our conversation on Monday with complex numbers, and we said a complex number can either be expressed in rectangular form, or it can be expressed in polar form, right? It's the same number. It can either have a real and an imaginary part, or it can have a magnitude and a phase, and it's the same complex number. And we even had a relationship for going back and forth between the two of them, right? We said that A, the real part was m cosine theta, and B was m sine theta. Did we not? I hope I'm not telling you guys anything you don't know already, right? I mean, I'm coming into this assuming that you've all seen complex numbers like 10 times before. Okay, good. I'm going to assume that that is true. Good. So I'm going to introduce a new form for complex numbers that you may not have seen before. It's going to help us a little bit. It's called the complex exponential. And a complex exponential works like this. I'm not going to bother deriving it. I'm just going to sort of have you take it on faith for now. If you want to know its sort of derivation, I don't know, someone in the math department can explain it, I'm sure. But basically it works like this. M angle theta, that's a complex number, can also be represented as follows. You can say that m e to the j theta. So m, same magnitude as your complex number, and then you have e to the j theta. And the definition of that is like this. That is equal to m. So now your e to the j theta is equivalent to cosine theta plus j sine theta. So this is just, so all I'm adding here that you don't already know, so this is a complex number. And if you take that complex number and convert it into rectangular form, what do you get? You get m cos theta plus j, where is it, j, m sine theta. So all I'm doing here and here, this is just going from polar form to rectangular form. So this part's not a mystery. Okay? The only thing that I'm adding to this that you may not know is that there's a more compact way of expressing it, which is this complex exponential, me to the j theta. It's just a different way of writing this. Okay? So far, so good? All right. Gets better. All right. So suppose I've got not just cosine of theta, but let's actually have like a real cosine. So let's say we had, I don't know, 6 cosine 5t minus pi over, 7. So what I want to do is I want to see if I can massage this to be in the form of a complex exponential. All right? So here's what I'm going to do. I'm going to pretend for a second that, so I've got this and I want to work this into a complex exponential. So what I'm going to do is I'm going to pretend that what I've got is in addition to this cosine, I'm going to pretend that I've also got plus j sine 5t minus pi over 7, the same thing. So I'm going to pretend that I've got this imaginary hanger on. And you'll see where I'm going with this in a second. So I started with a cosine, and now I'm just going to add the sine, just for fun. Okay? We'll get rid of we added it. I'm going to get rid of it in a minute. Okay? But right now I'm just going to add it because it's going to make the math a little easier. So can I take this portion in the middle and write it as a complex exponential? Totally, right? I mean, does it fit this pattern? Yeah. So let's see what I've got. I've got 6 e to the j. And now what goes next to the j? Good. 5t minus pi over 7. Okay. Now, I'm going to do 2 more steps. First thing is I'm going to distribute the j into this expression. So that's going to be 6e to the j 5t minus j pi over 7. Can I do that? Is that a legal move? Right, that's just good. That's just distributing the j. And then I'm going to do one more move where I'm going to break up my exponential, like my sum of exponents, into a product of 2 exponents. Can I do that? Right. So can I rewrite this as 6e to the j 5t e to the minus j pi over 7? Can I do that? Right. If you've got x squared times x cubed, what does that equal? X to the 5th, right? This is the same move, right? If I've got 2 things and I'm multiplying them together, I can just add their exponents. So I'm just doing the backwards of it, right? I'm taking x to the 5th and breaking into x squared and x cubed.
Would you have to put a bracket around that so that the n like 6 below?
So the what now?
So that 6e.
Yeah.
You have to put 6 below the second exponential.
No. If I did that, no, I don't. It's just they're just all multiplied together. There's no bracket necessary. Okay. So that's the worst of it, and I'm going to do one final little move here. I'm just going to rearrange it. I'm just going to take this term and this term. I'm just going to swap them because I'm weird like that. Okay, I'm just going to swap them. So that's going to give me 6e to the minus j pi over 7 times e to the j 5t. So let's stop for a second and look at this expression. So what this term is telling me, the e to the j 5t, that's telling me I got a cosine whose frequency is 5. We cool with that? Good. This is telling me the magnitude and the phase of my cosine. Yes?
How's that frequency 5? How does this go negative?
Well, here's my frequency, right? It's 5. 5 radians per second.
Okay. Oh, okay, the radius.
Right. 5 is just radians per second. Okay. So this tells me that I have a cosine at 5 radians at omega equals 5. And this tells me how much of that cosine I have. How much do I have? Well, I've got 6 units worth of amplitude and minus pi over 7 worth of phase. And with this expression, this hanger-on, we're going to call that a phasor. Now, believe it or not, you already know enough to make mincemeat out of that RC circuit. So here's what we're going to do. What do I do if I want to get my cosine out of this expression? What's that? You're almost right. What'd you say?
He said.
Oh, he said. Just take the real part of it, right? I mean, look what I started with up here. I had 6 cosine 5t minus pi over 7, and I just added on this bit that I didn't need. The reason I added this bit that I didn't need is so that I could take my cosine and represent it as a complex exponential. So when I'm done with the problem, all I need to do to get my cosine back out is just take the real part of this expression. So you'll see what I mean in a minute. We're going to do an actual example with real numbers from end to end, and hopefully you'll see what I'm trying to get at. So let's leave this circuit here. And let's come up with some numbers. So, and I'm going to try to get numbers that are going to make some sense. So let's pick a resistor of a kilo ohm. No, I've already lied to you. Okay, I want a resistor of 2 ohms, a capacitor of 1 farad. This is mathematically easy, we're not building a 1 farad capacitor, unless you want to see a cool explosion or something. Okay, and let's let my input voltage equal cosine of 1 over 2 cosine of, let's try 2t. Let's try 3t. Okay, I think I got it. So, my input voltage is cosine 3t, my resistor and capacitor as such, and our goal is to solve for V out. Are you with me? Good. So, here's what we're going to do. Instead of trying to solve for the solution when the input is cosine of 3t, I'm going to instead express my input as a complex exponential. So, instead of solving this problem, I'm going to cross it out. I'm saying, okay, whatever, we'll get back to that. What I'd really like to do is to find my output when my input equals 1 angle 0 e to the j 3t. So look what I've done. Look what I've done. You remember how before I added that j sign that I didn't really need? I've basically done the same thing here. What do I got here? I've got a cosine whose frequency is 3. How much of that cosine do I have? What was the magnitude of the amplitude of my cosine? Right? My amplitude was 1, so there's the 1. And what was my phase angle here? Right? It was 3t plus 0. Okay, so there's your 0. And that's my input phasor. Okay? That's my V in expressed as a phasor. Now, so I told you something important earlier in the class. I said that whenever your input is a cosine, your output is a cosine at the same frequency. Is it not? It is. All right. Okay. So I claim the following. If my input is this, then it must be true, because we've argued that this business of the cosine of the same frequency, my output is going to be some cosine at the same frequency, but the only thing that's going to be different is what? The amplitude and the phase, which I can express conveniently as a phasor. So let's call this, I don't know, V out, how am I going to express this as a, let's call this A, okay, where A has got some magnitude and some phase that I would like to know. So let's say A is a complex number that's got a magnitude and a phase. Yes? That's a 1. All right. So I'm going to assume that my output is a cosine at the same frequency. The only thing that's unknown is the phasor of that cosine. The phasor which tells me the magnitude and the phase. Are you with me? So we're done with this problem once we know the magnitude and the phase of this phasor. Yes? What's that? The 3 is the frequency, right? That tells you, this is acknowledging that my output is going to be a cosine at the same frequency as my input. Are we cool? Call me out if you're not. Like, let's argue about this before it gets worse. What's that? Yeah, it's got to be. That's the whole point of this, because it's going to be this is going to be a filter, and a filter by definition is going to change. Your output is going to be a different amplitude than the input, depending on whether it was in the pass band of the filter or the stop band of the filter. Okay, back to your differential equation. We know that V in equals this expression, V out equals this expression, where A is an unknown that we have to solve for. And what do I still need to sub into my differential equation? I still need V out prime. Okay. Well, let's see. If V out equals some unknown complex number A times e to the j3t, what do you think V out prime equals, the derivative of V out? Right. Good. 3j a e to the j 3t. You good? Just took the derivative. Do I have everything I need to substitute into my differential equation now? Look what I need. Do I have V out prime? Yes. Do I know the value of RC? Yes. Do I know V out? Yes. I know RC and I know V in. So all I'm going to do now is substitute into my differential equation, and hopefully I'll be able to massage the math so that I can solve for my unknown quantity, A. We on the same page? I assure you this is the easy way, right? If you saw the hard way, you'd pass out. So let's try this. So doing our substitution into the differential equation, we get 3j, I'm already lost, 3ja e to the j3t plus, now we need 1 over rc. Well, that's easy. RC is 2, so 1 over RC is a half. So plus a half. So it's a half V out, where V out is A e to the j 3t equals a half times my input, which is 1 angle 0 is just 1, right? It's just 1 e to the j 3t. Okay. Now what? Any takers on what happens next? Again, my goal is to solve for A. Yeah, the a to the j3t is common to all three terms. So can I divide it out? You bet. Look how easy this problem just got. I can divide the e to the j3t out of each term. So gone, gone, gone. What I'm left with is 3ja plus 1/2 a equals 1/2. Can I solve for a?
Yes.
Yeah, totally, right? Even I can do this. Multiplying through by 2 would be a start. How about we factor out? So let's do two steps at once. Let's multiply through by 2 and factor out an a on the left-hand side. Can I do that? So if I do that, okay, let me start by factoring out the, let's start by multiplying through by 2. So that gives me 6ja plus a equals 1. Wow! It's getting easier. Did I do that right? Good. Factor out the a. So now I've got a times 6j plus 1 equals 1. And therefore a equals 1 over 6j plus 1. Cool! What does that mean? Right? It's a number. Am I still any close? You know, my goal is still to know what my output was. So, at the beginning of this problem, I suggested that my output would be, that what I had to know was the phasor for my output. Okay? And a phasor has a magnitude and a phase. Well, here's my phasor. What I really need to do to interpret this properly is I need to basically rewrite this as a magnitude and a phase. Right? I mean, this is a complex number, right? You could put this into your calculator and it would tell you what it equals. So in order to interpret it, we need to know its magnitude and its phase. So, all right, well, what is the magnitude of A? 37. Right. How do we always get, if you've got a plus jb, how do you get the magnitude of that? Square root of a squared plus b squared. What if you've got a fraction? What if you've got two complex numbers like one on top of the other? What's that? Flip it. Yeah. It's the same. I don't know. Some mathematician somewhere probably cares. I don't. Okay, if you've got two complex numbers like in a fraction, like if you have a plus jb over, I don't know, c plus jd. What's that? No, not complex conjugates. It's always going to be the magnitude of the numerator divided by the magnitude of the denominator. That's the magnitude of the whole thing. So if this was your complex number and I said take the magnitude, you'd say square root of a squared plus b squared over the square root of c squared plus d squared. So, applying that knowledge to this complex number, give me the magnitude of the numerator divided by the magnitude of the denominator. Magnitude of the numerator, magnitude of 1 is just 1. The magnitude of denominator, root 37. Okay. Good. So let's get my phase angle now. Does anybody remember how to get phase angles? Yes. Square root of the real part squared, which is 1, and the imaginary part squared, which is 6. So 1 squared plus 6 squared. 36 plus 1, 37. You don't, well, yeah, it's you don't take the square of the j. You just take the square of the coefficient of the j. Okay, phase angles of complex numbers. What's that?
Tangent inverse.
right? You get inverse. So if I've got A plus JB, what's the phase angle? Inverse tan of B over A, imaginary part of a real part. And what if I have a fraction like this? How do I get the phase angle of that? What's that? Somebody said it. Subtract, exactly. It's phase angle of numerator minus phase angle of denominator. So if I gave you this expression and I say get the phase angle, you'd say inverse tan of B over A minus the inverse tan of D over C. Ooh, this chalk got small. All right, what's my next least worst option? Sometimes they leave a thing of chalk out here. I guess not. Times must be hard. Okay. Okay, so I'm back to this problem. So I need phase angle of numerator minus phase angle of denominator. So let's start with the numerator. What's my phase angle of my numerator? I'm hearing zeros. Can somebody confirm, deny, debate? Right? Phase angle of 1, that's really 1 plus 0j. So that's inverse tangent of 0 over 1, and inverse tangent of 0 is always 0. Another way to think about it is that if this is your complex plane with reals and imaginaries, where is the number 1 on that plane? Here's the number 1, right? The real value is 1, the imaginary part is 0. What angle does that have? 0, yes.
You're kind of listening to whatever you're doing with the tangent.
I'm sorry, I can't hear you.
You're kind of listening to what you're doing with the tangent. It's not really following.
This tangent?
Yeah.
This property of complex numbers? So let's say that's your complex number, right? And this is the angle that you wish to find. So this is so let's say this is A plus JB. So the real part is A, and the imaginary part is B. The phase angle of this is just by trigonometry argument, is the inverse tangent of the opposite side, which is B, over the adjacent side, which is A. That's it. That's all I've done.
Looks like you're subtracting it, that's all.
Yeah, because you've got two of them. Because when you've got a numerator, when you've got a complex number in the numerator and a complex number in the denominator, and I say what's the total angle, what's the total phase angle of this? The way you do it is you get the phase angle of the numerator by this equation and subtract from that the phase angle of the denominator, which you also get from the same equation. Okay. So let's see if we can seal the deal here. So we said phase angle of the numerator is 0 minus the phase angle of the denominator, which is the inverse tangent of, right, imaginary part of a real part, which is 6. Okay, can somebody hook me up and tell me what is 1 over root 37? Help a guy out. I'm guessing it's about 0.164. I was going to guess in that neighborhood. Okay, and minus inverse tan of 6. Make sure your calculator is in radians. Degrees are dead to you now.
1.406.
Negative 1.406. Can I get a confirmation on that? Yeah, and what are the units of 1.406? Radians. So, in other words, when we solved this, we got A to be 1 over 6j plus 1. Really, another way of writing that same number is 0.164 angle minus 1.406. Right? This and this are exactly the same number. Exactly. In fact, if you'd gone to, I'm sure your calculators all do complex numbers. If you did 1 plus 6j and took the reciprocal of it, I'm pretty sure your calculator would tell you that you got this magnitude in this phase. Right? We just sort of did it by hand so we could kind of understand how the pieces fit together. Okay. Shall we finish? So, when we started this problem, I asserted that your input signal was 1e to the j 3t. What you're now telling me is that if my input is e to the j 3t, my output is 0.164 angle minus 1.406 e to the j 3t. Okay, and so that's the phasor that we solved for. But that wasn't really the problem I asked you to solve, right? The problem that I asked you to solve was, what's my output when my input is cosine 3t? That's what we started with, right? So, can I use this to tell me what is my output for when the input is just a cosine? Yeah?
Going back to the solution.
Yes.
we got 0 comes from 0 minus tan inverse 6. Where
Yeah.
does 0 come from here?
The 0 is the phase angle of the numerator. See how there's a 1 up there? That 1 has a phase. You can think of 1 as a complex number, right? 1 is really the complex number 1 plus 0j. And it's got a phase angle, and that phase angle is 0.
Okay.
You can't ignore that. You will get the wrong answer if you ignore that. What is e to the j3t? We talked about that, right? Isn't e to the j3t really just cosine 3t plus j sine 3t? Didn't we say that that was true? And in the beginning of this problem, didn't I say we were going to add the sine j3t just to make life a little easier? Okay, it made life a little easier. Now we're done with it. So just as easily as we added a complex part that we didn't need, now we can just drop the complex part that we don't need. Okay? So basically what I can do is I can say, let's just forget about the complex part. So really, what my output voltage is 0.164 angle minus 1.406. Actually, let me rewrite it like this. Okay. Cosine of 3t, right? Because I can just dump the complex part. Because I didn't really have the complex part to start with. It wasn't really there. I just added it so I could sort of make the math a little easier. Okay, so what I'm telling you here is my output is a cosine with this frequency. What's the amplitude of that cosine? 0.164. And the phase? Minus 1.406. So putting it all together, my final output voltage is 0.164 cosine 3t minus 1.406. Done. This will get easier. It has to, right? It can't be any worse. Yes?
Pretty far back with a Vn equals 1.
Yes.
So the theta is going to be in radians.
Correct.
So if, say your magnitude was 3
Uh-huh.
to begin with, it would just be 3 times the radians, and that's what goes.
Right, right. You mean, sorry, if this was a 3 instead?
Yes.
If this was a 3, you would just triple your output.
Okay.
Right. It's just a linear multiplier. Absolutely. That was a lot of steps. And I've got 5 minutes left, and we're going to try to simulate this and see if we can get the right answer. What we're going to do when we convene on Friday, so what we've done here is an example with numbers in it, okay? Which is cool because it actually lets us like touch all the pieces of the problem, right? We didn't have to, I didn't like put in any variables. We just did numbers from beginning to end. And now we can actually run a simulation and see whether or not our output is in fact that. But what I want to do on Friday is we're going to replace all of this with variables. So instead of letting r equals 2 and c equals 1, we're just going to let r equals r and c equals c. Okay? And instead of sticking in some frequency omega, like instead of putting a value in, like we put in omega equals 3, we're not, we're just going to leave it as omega. And then we're going to analyze our circuit and see what it tells us. All right, are we up yet? Okay, so let's give this a whirl. Just shout at me when you can see the screen. Somebody want to get the lights maybe? Thank you. Okay, so, hey, here's an RC circuit. Let's just modify these values a touch. So let's set my capacitance equal to, hold on, let me see if I can resize my screen a little bit. So let's set my capacitance equal to 1 farad, my resistor equal to 2 ohms, and I'm going to set my input to be a sine wave at, we said 3 hertz? No, we said 3, well, cosine and sine is the same thing. You're going to see in a minute why that doesn't make any difference. So what's my, we said 3 radians per second was my frequency, right? But here it's making me express it in hertz. What do I do? Right, I do 3 radians per second divided by 2 pi. That'll give me my answer in hertz. So what is that? If I do 3 divided by 2 times 3.14, oops, that gives me 0.477 hertz, 0.4 and then 3 sevens. So 0.47 hertz. So this value in hertz is the same as having 3 radians per second. So that's it. I should be able to simulate it. So let's see. I'm going to run it for maybe 5 seconds. And I'm going to use a 1 millisecond time step. I'm sorry? Ah, thank you. That would have taken me many days to figure out. Let's run it for a little longer. And I also want to put my input signal here. All right, so in a second it's going to be done. Now it's plotting. Come on, MacBook Air, you can do it. Okay, now on Friday we're also going to talk a little bit about what's going on right here in the beginning, but we'll get to that. So, is the answer what we expected? My input signal has a magnitude of 1. What were we expecting to be the magnitude for my output signal? 0.164. Let's have a little zoom in here. Actually, let's hide. Okay, if I have my input, my output is, oh, look at that. 0.163. As advertised. Okay? Obeyed comes through. Now, what about the phase shift between them? You said sine, I said cosine, right? Does it matter? No, it's just a phase difference between them. So I've got 3 minutes left, and we're going to calculate that. 3, 2, whatever. Is it going to zoom? Yes, it is. Okay. So here's what I want to do. We might have to finish this on Friday at the beginning of class. So, but let's just write these numbers down so we can at least start with this. What time, so for this particular peak of the input, it appears to peak at time t equals 42.37 seconds. So somebody write down 42.37 seconds. Is that really that? Ooh dear. Oh no. Oh no. Sorry. It's like the world's slowest plotting. Okay. We said 42.37. Okay. Let me just bring that up again. So the input peaked at 42.37. Okay, screw that. 40.2. There it is. My input's height is 1 when the time is 40.30. Okay, now let's see what time the output maximizes. The output maximizes at 40.77 seconds. So what's the time difference between the two of them? So we said 40.77. And what was the first one? Sorry?
42.37.
No, we erased that one. 40.30, just like that? Okay, so the time difference between them is 0.47 seconds. When we start class on Friday, I will demonstrate to you, or maybe you will have demonstrated for yourself and someone can explain it to me, how 0.47 seconds does in fact correspond to the predicted delay of minus 1.406 radians. Right? Because that's what it's telling me, right? The equation says you should expect the output will be delayed relative to the input by that many radians. Okay? Now, I've just measured that delay, but I didn't measure that delay in radians. I measured it in seconds. But they should be the same thing. So when we start class on Friday, somebody will tell me why that makes sense. Thank you. See you on Friday.